Using the knowledge that we have learned on optimization of pharmaceutical formulations, we will use this knowledge to learn how to prepare optimum tablets. Tablets are considered most popular dosage forms, and this is because of the portability and ease of taking the medication. And also they are relatively easy to make on a larger scale. Tablets are made up of powders that are pressed into the desired shape. They contain a drug with fillers, binders, disintegrants, and lubricants. All those are essential ingredients or components that are important for the tablet to work in a good way. So, based on the balance of those components, it must be strong enough to handle, but when it's taken, it should break apart in the stomach. And then the overall quality of the tablets will depend on how you mix and how you press the ingredients. How do we make tablets? As you can see here, you get the different components are mixed together, and there will be a tablet press that will press the components together to form the tablet. So the first step here is to mix the powder together and blend the components. And then in some cases we could granulate the tablets, and that basically means we make the powder into clumps, and this is to make sure we end up with a powder that can flow well inside the die of the tablet press. And this will be followed by a process of compression, and this is in which we press the powder in a die at high force. And sometimes some of the tablets we can coat them, so we add a protective or colored layer. This is sometimes needed to protect the components from, for example, moisture, or perhaps in some specific tablets we add these layers to improve the taste of the tablet. Uh, the process called direct compression, and this is the simpler kind, where we don't do granulation as mentioned above. And this is a simpler way, so you could potentially, depending on the powder, whether it can flow well, can it be pressed and form a good tablet, then maybe you don't need to go through granulation process. In the process of wet granulation, which we mentioned earlier, the dry powder is mixed with some amount of water and with the binder, and will lead to formation of what we know as granules. These granules are then fed into the tablet press and compressed. And you can see here the most important part is to add the binder solution. So basically that will hold the parts of the powder together, and that will help form these granules, and this ultimately will help having a good tablet. It's important to understand the key components or ingredient and their role into tablets. So if you look into this diagram, that just explains the process of forming the blending the powder together to ensure uniformity of the powder. And the first thing here is the active pharmaceutical ingredient, and basically that means the drug. In many cases we need to use a filler, and this is because we need this to bulk up the tablet to a size that can be taken by the patient. Sometimes the dose is very small, so we need to make sure we have a filler. The filler will be very important in this case. And then we have a binder, as we mentioned earlier, and this acts like more or less like a glue that just basically holds the powder together. And as mentioned before, sometimes we don't need to go through granulation process because we can do just direct compression of the powder itself. And then what we need is to have a disintegrant, because once the tablet is pressed, that will require some component that will help for the tablet to break apart in the stomach. And this is the role of the disintegrant. And then finally, we need a lubricant. And the idea of the lubricant, it will help with the flow into the tableting machine. Basically, it will stop the powder sticking and to make sure the powder you end up with is uniform and there won't be any batch to batch variations. So the question here, what can we change? Or in other words, what are the variables that we can control? So here are, as you can see here, different types of variables that we have discussed before as important factors in the process of optimization. So for example, we can change the disintegration or the disintegrant amount as a percentage. And we said here earlier the disintegrant is important for the process of the tablet breaking apart in the stomach. So you can change that. And the other thing is you can change is the compression force, because that will control how hard we press the tablets. Other options such as the binder amount or the mixing time or the lubricant percentage. So basically binder amount, we said that could be important for a granulation process. The mixing time and the lubricant, they go hand by hand. So what happens here, the lubricant is often used or is always used at the end. So basically you need to mix all components together, and after everything is mixed at constant time, you will add the lubricant. And the time you add the lubricant or mix with the components can be varied, because the lubricant will be coating the powder, and that lubricant will help with the compression process. And for the purpose of optimization, we choose two variables to study using factorial design. You can of course choose more than two variables, and we call those independent variables. If you have not, if you have not, or you're not familiar with the term dependent and independent variables, then I suggest you go back and check the earlier videos to understand these concepts. It's very important that you understand these concepts, otherwise it will be difficult for you to learn or to understand the following points we're going to discuss. And then when we choose two variables, we need to make sure everything else is constant. For the selection of experimental levels, we mentioned earlier, we will choose two dependent variables. And for the tablet, we will choose the disintegrant amount or the level or concentration, as well as the compression force. Of course, you can choose any other variable that you wish. But for this exercise, we'll choose those two. So x1 is disintegrant amount, and the x2 is the compression force. And as you can see here in this diagram on the right, you can see that there are three levels that been selected. And then here you can see that there is a low, medium, and high. And we said it's very important that you choose those levels at equal intervals, and that you can see here clearly. We chose 2, 4, and 6, so there are 2% increment. And likewise for compression force, we chose 5, 10, 15. We can change this to a standard system, and we said that could be -1, 0, and 1. So basically, we just put everything on the same scale. The first dependent variable that we can choose to assess our tablet is the hardness of the tablet, which is basically the crushing strength. Basically, you apply some force, as you can see here, until you crush the tablet. And then the force needed to break a tablet, in this example here, we target between 50 to 100 newtons. And the idea of this is to make sure to measure the hardness of the tablets to ensure that it will tolerate within a target value. The second test is the friability. And here, as you can see in the diagram, basically we rotate the tablet into a friability tester, and this is the idea is we measure how much of the mass is lost. Sometimes the tablet is not well compressed or the components are not mixed well. Some of the tablets might crash or break apart. That's also a possibility, and that often means you've got to optimize your components better. And here, as you can see here, then there is on the weight as expressed as a percentage, and there is a limit for that loss. So in this case, we put a limit which is 1%. And you do a number of rotations and you plot the loss in mass. That is how you do a friability test. Of course, you have to follow the pharmacopoeial standards to assess the friability of tablets. The third dependent variable is the disintegration and the dissolution time. So basically the disintegration is the time which is needed for the tablet to break apart, and this is the first process in the tablet dissolution. This should be followed by a dissolution test, which is shown on the left side here on the dissolution apparatus. And then we should aim, and again that depends on the drug, but in many cases, as specified by the pharmacopoeia, it requires more than 80% to dissolve within, in this case, around 20%. So that means the drug is suitable for example, immediate release. So those two dependent variables are very important to assess the quality of the foam tablet. Here is a summary of the tablet quality test that we mentioned earlier. We mentioned the hardness, and we said this is the force needed to apply until the tablet cracks. Should we aim between 50 to 100 Newton. Friability, and this is basically the weight loss, and we say that it should be below 1%. Disintegration is the time to break apart, and this is followed by dissolution test, and that is the time for the drug to be released. And these two often should be checked in the pharmacopoeia because they depend on the drug type. And finally, there is a test which is weight uniformity. So these should basically mean the tablet should have the same weight, and a difference or a variance of 5% is the maximum that should be allowed. One thing we could do to optimize all these properties is, of course, as we mentioned before, is to use factorial design and the model dependent optimization that we mentioned before. So we basically have a model or equation that help to understand the correlation between the dependent and independent variables. So for example, increasing the disintegrant, it's expected to faster breaking up of the tablet or disintegration, or and followed by dissolution, but then at the same time that may make the tablet weaker. If you increase the compression force, you get a stronger tablet, but slower to disintegrate and dissolve. And then interaction, which is the interaction between those two dependent variables. At high force, disintegrant works less well, and then there should be like a kind of a sweet spot. So basically we balance strength and the disintegration time. And the way to balance or to find this sweet spot is use the contour plot. And that basically we overlay the two maps that we generate, 2 or 3 maps we generate from the dependent variables to find the best outcome of where we call also a safe zone.